Okay. Hello to those of you watching this video in the future. It's semester 2, 2022, and this is a revision seminar for Statistical Practice I in all of its different flavours and the various different degrees that it's part of. Statistical Practice I is a statistics course, and most disciplines have one. And every one of them is a little different. And so what that means is that when I do a seminar like this, I have to check what's in your course, because it's different to what's in the economic statistics course, and it's different to what's in the computer science statistics course, and so on. And so I just need to be absolutely certain what things are in it. And also, it is just good for you to try and remember what's in your course. So we're going to do a bit of a brainstorm on distributions to start with. Just to make sure we cover everything we can think of. So, type in the chat or put your microphone on and talk, or just say what distributions or what information about distributions have you seen in this course? This is a good activity to do when you're trying to study, so just try and brainstorm these things. So I'm going to shut up for a couple of moments and let you think about it, and then feel free to tell me what you've thought of. All right, I've had one. Thank you to our brave person who's given me the first one. You mentioned some the other day.
About trying to understand the difference between normal and the binomial, and I have no idea about
Binomial, F. Right, having heard normal, binomial, F, does anyone have any other names of distributions? We've got a T. Anything else turn up in this course? Z. I have a guess that in this course there was also a chi-squared. Did you do the chi-squared test?
We did. I didn't know that fell under distribution. There we go.
So it's the name of a test, but it's also the name of a distribution. I think that might be everything, except that I just want to add that Z is a kind of normal distribution, usually. And we'll get to that in a minute. I'm glad that someone mentioned this center and spread thing. So this is information about a particular distribution, or no particular distribution, just what's in your graphs and charts. And these are names of specific distributions that statisticians know about. And so now I'm going to talk about distributions from this information. And I'm also going to say something, is that these ones are the ones that turn up as test statistics during hypothesis testing. These ones, not so much. All right. So do people feel like we need to add anything else to what we've got here? Yep, so over here when you're talking about things, cool. All right, I reckon that's enough to be going on with. If you think of anything along the way, feel free to tell me as we go. But for now, this is a good start. Okay. Right, so let me talk about distributions as an idea in statistics, and then I'll talk about both flavours of this along the way. So I'm just going to say this was a brainstorm. When I put the notes online, I want people to know that that's what this was. Okay. That is not how you spell brainstorm, it's got an R in it. Okay. So a distribution, the word distribution in statistics is trying to get at the idea of what all the possibilities there are and whether some of them are more likely than others. So like a distribution is a thing, but what it is a description of, yep, I'll put that shape, is a description of what all the possibilities are and how likely they are relative to each other. So no one ever actually describes, in almost all statistics courses, no one ever says what they mean by the word distribution, but that's what it means. So in ordinary English, distribution means the spread outness of something. You talk about the distribution of a newspaper, you say who the newspaper goes to, and you talk about the distribution of koalas in the South Australian bush, and you say, well, where are there koalas, where are there not koalas? So distribution is that idea, the possible numbers, all the possibilities, and when we mean not possibilities, we mean the possible numbers that could happen. The possible numbers are spread out in a certain way, and some of them are more likely than others, and that's what we're trying to get at when we talk about a distribution. So there are two very different ways that we talk about distributions in statistics. We talk about the distribution of your data, and we talk about probability distributions. And when you're talking about the distribution of your data, you tend to use different kinds of words than when you talk about probability distributions. So it's just worth noting the context that you're in. So when you started in this course, right at the beginning, the first thing you did was talk about, actually you probably talked about different kinds of variables, didn't you? You talked about quantitative and qualitative, no, categorical? Yeah, and those sorts of things. And after you did that, then you talked about drawing, histograms and scatter plots and those sorts of things. So a histogram is a way of displaying the distribution of your data. That's what a histogram is for. So I'm just going to talk about the distribution of data first. So when you're talking about distribution of data, your assignment or exam question would normally have a phrase in it, something along the lines of describe the distribution or compare the distributions. Yeah? Those two commands are about making a description of what all the possibilities are and how likely they are relative to each other. That's the kind of thing you're supposed to be, that's the question you're answering. What are the possibilities and how likely are they all? And so the first thing you could do to describe a distribution is to say, well, all the numbers are between 10 and 500, right? That's a thing that you could say. And you could try and say, well, most of them seem to be between, 50 and 70. That's another way of describing distribution. And these are the first things that you would naturally do if someone said to you, tell me what the possibilities are and whether some of them are more likely than others. That's the first thing you'd say. You'd say, well, they're all between these numbers and most of them are between these numbers. Now, that's great, but your lecturers have very specific things they want you to mention when they ask you to describe a distribution. They want you to mention exactly what our friend mentioned earlier, which was where the location of the centre is, how spread out they are, whether there are any outliers, and the shape. Now, spread is really only relevant for comparing distributions. You can't really talk about it for a single distribution, other than saying, well, they tend to be between these numbers and these numbers. Yeah. So your lecturer wants you to talk about shape, location, spread, and outliers. And some people call this centre. It's the same idea. Where is the most common things? Okay, but just stepping back, if you just have a list of numbers, you can make a guess at least the spread. And you can make a guess at outliers. Outliers are numbers that lie out from the rest of the data. And if you just had a list of numbers, you could make a good guess at which things were outliers, because you could read them all and go, oh, well, most of the other numbers are between 0 and 100, and this one's 200. It's definitely an outlier. But it's much easier to do these things if you can see them. And so what we do is we draw an x-axis, traditionally, and you put a scale on your x-axis, and you locate all of your numbers on this axis. And the computer usually does this for you, but you can literally just draw a mark where all of the different numbers are. And so your data might be spread out like this. And maybe there's nothing just here. And what the computer does is you tell it to cut this into pieces, or it does it automatically. It makes a choice of its own to slice this into bits and count how many are in each zone. And it says, well, there's 1 in this zone, and there's like 5 in this zone, and there's 7 in this zone, there's 4 in this zone, there's 4 in this zone, there's 1 in this zone, and that's a histogram. And that's what a histogram is. And we use R in this course, right? In R, you can control how wide these things are and how different they are. And these things are called bins, by the way. And so when you're in R and you do the histogram function, you can say bin width equals 10 and it will make them 10 wide. I'm pretty sure in your exam you're not going to be asked to write R code, but I just, that doesn't sound like something the maths lecturers, the lecturers in the School of Maths do. They may give you R code and ask you to interpret what it means. They'll usually give you the thing that the R produces and say interpret the output, but they won't normally get you to just write R code, because they know that people who actually use R never do it in an exam situation. You can always look it up. So yeah, and you always have R to tell you when you've missed a bracket, right? Or when what you've done doesn't make any sense. So they don't want to test that because they've tested that enough in the assignments. Just warning you now that that's usually the case for this course. Your good standard for the way that they ask you to interact with R in the exam is to look at the practice exam they've given. and see how much R information there is in it, and that will be similar to your real exam, just as advice. Anyway, that was an aside. And so this one I can see that most of the, let me just put some numbers in. This is pretend data. I can say for the spread, the data is spread between 5 and 40, right? It seems to be located the centre seems to be located between 15 and 20, because that's where the peak is. So that's what I would say. And the shape, it has a single peak, and so it's unimodal. Is that a word that they use in this course? Yeah. And it possibly might be longer on the right-hand side than on the left-hand side, which means it's right skewed. So they're all the things I could say about this, and I would say them in a couple of sentences. I'd say something like, unimodal with possibly right skewed. The centre is located at between 15 and 20. The spread is between 5 and 40. Now, without doing more calculations, I could calculate a standard deviation or an interquartile range and say, well, that's what the spread is if I wanted. There appears to be an outlier at approximately, 38? Because it's quite a big gap between that and the rest of the data, and maybe, at about 6 down here. So this one's quite a long way from the rest of the data. This one's quite a long way from the rest of the data. We can't be, if all we saw was the histogram, we wouldn't be able to tell that. We'd probably have to draw a box plot to get it to tell me where it thinks the outliers would be. And so the box plot would be like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So halfway is about there. And then 1, 2, 3, there. There. And then nothing is flagged as an outlier by the box plot. But whether a box plot tells you there's an outlier or not is irrelevant. If there's lots of, wait, I'm talking about too many things at once. Sorry. So I can talk about those things when I talk about the shape of a distribution, when I talk about a distribution. So the things that you can say about shape. So shape you can't tell from a box plot, you can only tell from a histogram. So you get that from the histogram. And this can have there's two things you can say about shape. You can either say it's symmetric or left skewed or right skewed. They're the three options of ways that you can talk about that feature, and symmetric things are the same on both sides. Left skewed things are longer on the left side, and right skewed things are longer on the right side. The word skew means pulled. When you skew things, you pull them and twist them, and so you've pulled it out on the left side. Yeah. Or possibly pushed. Either way, you pushed it out on this side. And the other thing you can say is how many modes it has. So a mode is one of these peaks. So if you want to talk about shape, you'll often say, well, it's symmetrical, unimodal symmetric, or left skewed unimodal, or left skewed bimodal, or right skewed unimodal, whatever. Technically, you can be bimodal and symmetric at the same time. It's just that the two humps are exactly the same as each other, one on each side. So you get to talk about any of those things. And you can never say anything that is just hard and fast. It has to be appears to be. Because all you have is your data. So it's like, it appears to be symmetrical, or it's approximately symmetrical, or it appears to be left skewed, or there is a suggestion of right skewness, or, yeah. All statistics, unless you are talking about theoretical probabilities, all statistics always has words in the sentence to suggest that you're not 100% sure. You'll say, there is evidence to suggest, or, yeah. But usually with these ones, because you are looking at a picture to make the decision, you usually use the word appears.
Seems like right. To have numbers which back up a hypothesis, but you have to use very non-certain words.
Yeah. So you are allowed to say there is very strong evidence that, not in this context, but later. But that's a very science thing, right? Because in science, in true and proper science, the only things that are the truth are your direct observations, and everything else is theory. And it may be a very well-renowned and theory that everybody believes is the truth, but it's always, all science always holds in reserve the chance to change your belief based on future observations. So gravity works the way gravity works, and we have some really good theories to explain how that works, but new observations may possibly change how we understand that, and we'll have a new theory. So it's very scientific to not ever say it just is, other than something you've directly observed, where you say, it is possible for monkeys to learn that they want to salt potatoes because I've seen it happen. Okay. That's shape. These are the sorts of words you say, and you pick one of these, and that should do the trick. And for location, you just say the majority of the data is here, or the center appears to be. Around the number x. Or you might say the mean is that x. I can put a number in that spot. And for spread, if you've only got one distribution, you'll often say most of the data is between here and here. Or you'll say the standard deviation is this, or the IQR is this. But most of these things you say about it is actually based on the pictures and not the numbers. But you can say that. And if you've got two of them, you could say one is more spread than the other. So you might say, oh, I don't know what we're measuring here today. So you might say that the amount of hours of sleep per day is more spread out for university students than it is for professional veterinarians or whatever. So that's sort of what you'd say for spread, that one is more spread than the other. And if there are two of them, you might say the center of one appears to be higher than the other, or further than the other, or whatever. And so it is okay to say, if it's got two modes, if you say it's bimodal, you're supposed to say it's bimodal with peaks at approximately this spot and this spot. here and here, for example. You might say something like that. There is no E in peaks. There is only one E in peaks, sorry. If you're going to say it's bimodal, you should say where the peaks are. Because those peaks correspond to the numbers that are most likely to appear. Because the histogram's counting the things that are most likely. And then finally for outliers, you just have to say there appear to be outliers at these places. And then mention them. And if there's like 6 of them, say there appear to be outliers in the range from here to here. Most people don't really care how you talk about these things as long as you mention the most important features. So the last thing to say about outliers, actually before I do that, does anyone want to ask any questions or add anything onto this? Cool. If you change your mind, just yell out. Last thing about outliers is your box plot can give you some indication of things that might be outliers. And so you can't see outliers in a histogram. Well, sometimes you can, because there might be like this huge gap where there's no bars and then there's a little bar over here. So you can sometimes see outliers in a histogram. So I'm not going to say that. But usually you look for outliers in a box plot. So when you do a box plot, what a box plot traditionally does let's put a few more in the middle here. What a box plot traditionally does is you count where the data is. When we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There was one there as well. Just a second. You find the middle. 1, 2, 3. That's the middle just there. And you draw a line there. And then you find the middle of this bit. About there. And you draw a line there. You find the middle of this bit. And you draw a line there. So since it wasn't one of the numbers, I draw it halfway between. And this is called the first quartile, and this is the median, and this is the third quartile. And then you draw a box like this. And you draw a line like this. This was your traditional original recipe box plot invented in 1977 by Edward Tufte. He was still alive. And spends most of his time making extremely large sculptures on his ranch in the USA. So this is a traditional box plot, but what you do is you go 1.5 of this distance here is called the interquartile range. So inter meaning between, quartile meaning these things, and range meaning gap. So this is the interquartile range, and it's a measure of spread. If one distribution has a bigger interquartile range, then you can say, well, they seem to be more highly spread. And this is the minimum here, and this is the maximum here. And each zone here contains a quarter of the data, because we cut it in half to figure out what this number is, and then we cut the half in half to figure out what this number is. 1/4 of the data is here, 1/4 of the data is here, 1/4 is here, 1/4 is here. And so a box plot is specifically designed to talk about how spread out each piece of the data is. So it's saying this top quarter is much more spread out than the second to top quarter. The most spread piece quarter of this data is the top quarter, the highest quarter. Yeah. So what the interquartile range can do is if we go 1.5 of this interquartile range from the third quartile, so that plus about this much, that gets us to here, and anything beyond that is marked as an outlier. So we get our IQR and we go 1.5 of that distance. And anything beyond that's marked as an outlier. And we'll go 1.5 of this distance on this side as well. And anything beyond this is marked as an outlier as well. And so the thing that the computer will show you will be this. Like that. So anything that's beyond this mark, it'll do as a dot, and it'll only make the line go up to the last thing that was within this mark. Yeah. And so the computer thinks this is an outlier. It's a potential outlier, like that. How do people feel about that?
So which should you be using if that was the way that you'd actually draw one by hand?
Do this.
Stick with the
So you'll stick with this one. This is your original recipe box plot, but then a few years after it was invented, we did this. And so this is what we do now, and this is what a computer would do. So if you were drawing a box plot by hand, this is what you would draw. But if you didn't have time to calculate this, then you just do this. So I will say something, that it doesn't have to be this way, sometimes it's this way, and you can read it either way around. So just as an example, if your box plot looked like this, and it flagged all of these as outliers, I wouldn't say they were outliers actually. They were really just part of a long tail. Because they're close to each other. Like none of them is very far from the next one. So the distance between the last data point that wasn't flagged as an outlier and the next outlier, they're all pretty small distances. So none of them has a big gap between it and the next one. So I would indicate that they're not outliers, they are part of a long tail. But what you would say is there are several potential outliers which may be part of a long tail, and leave it at that. And just leave it at that. I don't expect them to get you to make a weird-ass decision like this in the exam, but you never know. One of the assignments this semester, you did the before and after data, and they both had these lots of outliers, and so I would have suggested people say there are several potential outliers in the box plots, but they might be part of a long tail and not actually be outliers. An outlier has to lie out from all the rest of the data, and there's not a big enough gap here, I don't think. But it's not like there's rules. Outliers are just a way of saying, just look at this because there may be something interesting happening here. Yeah. All right, how are we feeling? Cool. So just one last example of this. Something like that. Maybe just a second. Yeah, let's do that. So if you had these two histograms for two different situations, this is situation A, this is situation B, and this is like 1, 2, 3. Oops, 0, -1. Maybe these are temperatures, hey? Because there are to be negative. So if I was to compare these, and I would run through the shape, and I could say both appear to be right skewed, something like that. And I would say location of A is oh no, still talking about shape. We should say they both appear to be right skewed and unimodal. A, the location of the centre. Oh crap! How do we arrange this sentence? The peak is here, and the peak is here, right? So I would say that for A, centered around 3.5, but B around 1.2, 1.5, between 1 and 2. Oh crap. The data for A seem to be centered around 1.2, 3.5, but for B around 1.5. So A seems to be higher in general than B. The spread seems similar, except for those outliers. So without the outliers, this one's maybe possibly slightly less spread. But I would just say the spread is similar.
Would you then say the spread is similar? You wouldn't actually say
the
distribution is greater.
No.
Would you say so?
But you might say if this one had lots more columns than this one, you'd say, well, this one seems more widely spread than this one. But you could we could skip ahead and say without the outliers, A might be less spread than B. And then the other thing I'd say is there appear to be some outliers in the distribution for A, between 8 and 9 and 11 and 12. About 8.5 and 11.5. That's all I can say. I can't know exactly where they are because I don't know where the individual things are, but they're about that. There's big gaps between these. So I've mentioned all the things: shape, location, spread, outliers. Done. And so when they explicitly say to compare them, you have to not just say, you're just saying that no outliers in B. Right, okay. When you say to compare them, you have to not just say what you see, but also how they're similar or different. So they're both right skewed. And this centers this centers this, which means that A is higher than B. So make sure that you have at least one statement in there that says how they're different or similar, rather than just listing the means or listing the locations. So that's that. That's describing the distribution of the data you've got. And this is an entirely different thing from talking about the distribution of a probability distribution. And they're completely different things. So I'm just going to say, in the context of hypothesis testing, If they say, what's the distribution of the test statistic? They do not expect you to say anything about shape, location, spread, or outliers. That's not relevant to that discussion. And the way you can tell is they've said, what is the distribution? We're here we're being like, oh, well, it looks like it's this, it looks like it's this. If they want you to make a hard and fast decision, what they're asking you for is a name of a distribution. So I'm going to talk about that as well. So this was about describing how the data we've got is spread out, but then there's also probability distributions. And they're a different thing entirely. So, statisticians, even before there was a name statistician, and mathematicians have thought about these histograms and that sort of thing and noticed that some things tend to have similar sorts of distributions, similar sorts of ways of describing them, such as unimodal symmetric. And they've done some calculations based on probabilities. And so in a probability distribution, it's not just a description of all the possible numbers and how likely they are relative to each other. It's an exact description of how all the possibilities are and how likely they are relative to each other. So spread is about saying, well, you know, what are all the possibilities? And centre is saying, well, this one, they seem to be more likely to be here than elsewhere. But we don't use sort of likelihood words when we're talking about a distribution of a data. But when we're talking probabilities, well, that's what probability is for, likelihood. And so it's an exact description of all of the probabilities that go with all of the options. So it's still a description of what they all are and how likely they are relative to each other, but it's an exact description. Right. So the big philosophy of probability theory and statistics is that anything that you could possibly measure or write down has a probability distribution that in the fabric of the universe exists, but you don't necessarily know what it is. Right. So every time you record the height of a person, there is a list of possible heights it could have been and how likely they all are, and today one of them happened. Every time you roll a die, there's 6 options that it could have been, and today one of them happened. And that's the idea. And that the universe has a list of probabilities saying, yep, probability of 1 is 1 in 6, probability of 2 is 1 in 6, probability of 3 is 1 in 6, and so on. And you roll the die, and today one of them gets chosen. That's the philosophy. Everything has, theoretically, a list of what the probability of everything is. Anything that you could possibly measure or write down. That's important. It will come back in a minute. Okay? And so anything you can measure or write down has a probability distribution to describe what all the things it could have been and how likely they are. And some of those probability distributions have names and we actually know what they are? So when a statistician says, what is the distribution of this test statistic, they are looking for a name that says, oh, well, you know, statisticians have been investigating different kinds of distributions for some time, and out of all the list of distributions they've seen before, the one that I see today is a normal distribution. So it's not that different from bird watching, okay? Like, I saw a bird. What bird was it? It was a wedge-tailed eagle, right? So it's the same idea. Oh, this thing must have a probability distribution. Which distribution? A t-distribution with 5 degrees of freedom. Okay, so that's the idea. Wedge-tailed eagle is an eagle, but it's a wedge-tailed eagle. It's a t-distribution, but it's the one with 5 degrees of freedom. There's different kinds of t-distributions. It's that sort of thing. And telling a statistician it's a t-distribution with 5 degrees of freedom is giving them enough information to figure out any probability that they would want to figure out. Because they can go and look up the theory of how the formulas work to figure out the probabilities they want. And when computers were invented, they fed them all into computers so that they could figure it out without having to do the formulas. Because the formulas are really hard, and some of them don't even have formulas, and they can only be done approximately. So, yeah, so some of them have names. Some of them don't have names, and it's okay because there's just a list of what the probabilities are. So the distribution of numbers on 2 dice doesn't have a name, but we all know that 7 is more likely than 6, and rolling a 2 on 2 dice is much less likely than anything else, and just as likely as a 12. And so it doesn't have a name, but we still know everything we need to know about it. Okay. That's the philosophy. Works best with some examples. So the simplest, and therefore the least helpful example, is the one where there's only 2 options for what could happen, and each of them has a probability to go with it. E.g. class of 250 students, 10, no, 100, so they like cats, and 150 say they don't. This is a probability distribution already. If I randomly pick a student, if you randomly choose a student, then there are 2 things that could happen. They could either say they like cats, or they could say they don't like cats. So the probability that the student likes cats. Does this look like the probability notation you've seen with a capital P and brackets? Yeah. Is 100 out of 250. And the probability that the student doesn't like cats is 150 out of 250. That's it. That is the simplest possible example of a probability distribution. There are only 2 options, and each of them has a probability of their own. What is this? I multiply by 4, then. Okay. So that's what calculators are for. So just let me check that. Yes, okay. So this is the simplest possible kind of probability distribution. There are 2 options. One of them, either one of them happens or the other one happens, and one of them each of them has a probability, and the 2 probabilities add up to 100%. For some reason, statisticians don't like percentages in this context, and they prefer decimals. There you go. Over in economics, you'd be allowed to write this as 40%, but not in Statistical Practice I. I'm just going to check something. I've got an email and I just want to see if there's someone trying to get into the Zoom. Nope, okay. This is called a Bernoulli distribution, after the mathematician Bernoulli, who was the first person to put it in a textbook, so like to write about it. But they don't talk about this much in this course, but some courses they make a huge deal about it, and it really is not that important. I mean, just look at it. It's like, well, obviously there's only two options, but other distributions sort of use this as the standard. That there are two options, and if there's two options, they have to add up to 100%. It's basically it. So just in case you were wondering, this is called a... And I will say something else that's really important. No probability exists unless all the other probabilities are there. Like, if I didn't know how many students there were in this class, I would not have any clue what the probabilities were. And so, unless it's possible to not like cats, the probability of liking cats is irrelevant. So probabilities are always in comparison to something, in comparison to all the other options that could have been. And so if I have a student who likes cats today, the probability of that thing happening depends on, well, the not liking cats as well. So they're both there, even if I'm only interested in one of them at a time. I know that sounds like stupid philosophy, but like it's important to know that every probability is a comparison between all what you've got and all the things that could have been. Okay. Right. So statisticians have worked for a while to try and figure out different situations in real life, what the best guess at what the probabilities are in those situations. And a lot of situations where you measure individual things, it's on living creatures or even inanimate objects, it tends to be a normal distribution, which is why it's called normal, because it happens so often. But I'm going to get to that in a minute. No, I'll do it now. So if you measure, give me a second, the tail length of ringtail possums. Every possum, like, let's say they're adults, just to make sure that they're not going to change their tail length much over time. Every possum will have its own tail length, and different possums will have different tail lengths. And if you knew all the possibilities that could possibly be for ringtail possums, you can compare what you've got to all the ones that could have been, and that would be a probability distribution. And so you could ask yourself, how likely is it that the tail is 20 centimeters long? They're about like this big. That's 20 centimeters seems about right. So how likely is it the tail is 20 centimeters long or longer? The chances of it being exactly 20 centimeters long is going to be pretty slim, because it could be 20.03 or 19.7 or whatever. So the chances of getting an exact number is really tiny, but the chances of being near 20 might be bigger than the chances of being near 15. And that's what we're talking about with a probability distribution. And so if you do that and you think about your individual little ringtail possum, there you go. The ears are probably too big, but anyway, close enough. Just a second. Tail's curling the wrong way. Think about your individual ringtail possum, and every ringtail possum has a number for that tail length. And different ringtail possums have different lengths. Some of them have the same length. And when you draw all the possible lengths as a number line, You go, these are the short ones and these are the long ones. And you try and say which ones are more likely than which ones. And so you draw a height here, and it'll be taller if it's more likely to be in this spot and shorter if it's less likely. You'll get something like this. Possibilities. I love it. I'm so excited. This is only the second time in all the years I've done revision seminars that I've used possums as an example. The first time was because we were in the Darling West Lecture Theatre, and there were actual possums in the roof at the time. So we have, these are the possible lengths, possible lengths, fabulous. And this one is more likely than all the other lengths, and it's really unlikely to be over here and really unlikely to be over here and sort of middle likely to be here. And it's not, this height isn't a probability because there's sort of zero chance of being any specific exact number to like 7 decimal places. But it's much more likely to be between these two numbers than it is to be between these two numbers. And so what we have is that the height is sort of likelihood, and the area is probability. So this is called a continuous distribution, and this particular one is called a normal distribution. And it is very common for physical measurements of living or inanimate objects to be from a normal distribution. It's not always true. If you measure the size of grains of sand, they'll be skewed. And they will come from I can't remember what it's called, something else, log normal or something like that. But the important thing about your normal distribution is that it's the areas of the probabilities. Okay. And there is a formula for the height of this graph. But the problem with that formula is that while it's lovely, and it's what Desmos uses if you go to the graphing calculator and ask it to draw a normal distribution, it can't, there's no formula for the area, and the only way to do it is to approximate it with some very clever numerical calculus. So that's why we always have to get a computer or a table in a book to tell us this stuff. And so what will happen is that this thing will be what's called the mean, and then how spread out it is on either side, so how far it is where the hump ends and the tails begin, that's the standard deviation. And the standard deviation was invented specially for normal distributions, and then we borrowed it for all other distributions. So, yeah. So that's the normal distribution. And when I say the normal distribution, there's not just one. Possums maybe have a mean of 15 centimetres and a standard deviation of 3 centimetres. But maybe the tails of leadbeater possums is a mean of 20 centimetres and a standard deviation of 5 centimetres. So there's a different normal distribution for every mean and standard deviation. They're all the same shape. They all look to the naked eye exactly the same, and in fact if you literally just shrunk them and stretched them, they would be precisely the same. And they all have the same features of the center is higher, it's perfectly symmetrical, the sides are identical, and it gets shorter over here, and almost all of the probability is between +3 and -3 standard deviations. They all have those features, but because they're about likelihoods of actual numbers, they're not quite the same. Yeah. So there you go. So you need, so you might say, if tail length was capital T, then you would say a statement like T is distributed according to a normal distribution with mean 15 centimetres and standard deviation 3. You might say a statement like this. Have you seen this symbol in this context before? I asked some people in the Zoom, does this look familiar, something like this? Yeah, that's okay. So this, it is tradition to use capital letters for numbers you haven't measured yet. It's tradition to use capital letters for probability distributions where you haven't actually measured the tails of the possum today yet. Like, I haven't measured the possum. I'm thinking about all the possibilities. So when you're thinking about all the possibilities, you use a capital T. When you think about just today's possibility, you use a small t. Yeah. Can I just use L instead of T, because the T is going to freak us out when we get to the T distribution. Okay, so what this means when you read it aloud, you say that L is distributed as, that's what this symbol means, is distributed as a normal distribution with mean 15 and standard deviation 3. That's how to read this maths aloud. Yeah. You should always know how to read your maths aloud. As Mem Fox says, all good writing has been read aloud. She doesn't say it about maths, but it's still true. Okay, so Mem Fox as in the author of Where is the Green Sheep, that person. Sorry?
Who else?
Yeah. Not everyone knows who Mem Fox is, so just checking. They should. So this symbol is how we talk about things being distributed according to things. All right. So the other real life situation okay, so I said that anything that you could possibly measure or write down on any object theoretically has a distribution to describe all the things that could have happened and how likely they are. I catch 16 possums, measure all their tails, and find the mean of that 16 possum tail measurements. So I'm not going to make it into a proper question. I just want to, this is the situation that I'm thinking about. So $16 possums, right? I'm not going to draw them all. And every one of them produced a number of their own. They all produced a number of their own for their tail length. And then the group of 16 produced a number as well by combining these numbers together. All right? But I could have collected a different 16 possums. And in 3 years' time, there will be new possums that don't exist now that I could measure their tails, right? And so assuming that all possums for all time, or at least for a while, have similar tail lengths, there are other things that could have happened other than the mean tail length I measured today. So there are lots of different possibilities for what this mean tail length could have been. And a comparison between the possibilities and all the other possibilities is a probability distribution. So the mean tail length itself will have its own probability distribution of all the things it could have been. That's one of the big ideas of statistics. If I imagine all of 16 possums that could be, then there'll be lots of different mean tail lengths that could have been, and some of them will be more likely than others. That thing is, most people call it a sampling distribution because it came from a sample, and we got it by imagining all the samples that could have been. And so what might happen is that instead of having the number from a single possible mean lengths this time, maybe the mean will still be 15, and it will be, but averages of 16 possums tend to be closer to each other than individual measurements of individual possums. And so it won't be as spread out as the other one was, like that. And this standard deviation will be smaller than it was before. It used to be 3, and now it's going to be 0.75. Now, there are rules for how this works. The rule is that if x is from a normal distribution with mean mu and standard deviation sigma, then the mean of n x's, which you normally call x bar, is also from a normal distribution with the same mean, and the standard deviation will be that. We'll divide the old standard deviation by the square root of the number that were in the group to make the mean. I don't know if this formula appears in your course anywhere. It does appear in some courses. Bottom one, not so much. Yep. Yep. Now, I don't know if this appears in your course, so take it with a grain of salt. It's still true whether it's in your course or not, but I don't know whether they want you to know it. But it is true. All I was saying was not so much the exact formula for how this works, this is just for your own interest, but the fact that the means have their own distribution to describe how likely the means are and what all the possible means could have been. And that means of 16 tend to be closer together than individual numbers. So the idea is that this one's sort of spread out. This one's spread more widely than this one is. Yeah. Okay. And there is a theorem called the central limit theorem that says that even if for individual objects their distribution isn't normal, when you do a mean of enough individuals and think about all the possible means it could have been, that will still be normal anyway. So even if the individuals were like that, for example, which is not normal, and these are my possible, let's call them lengths. Even if individuals do this, for groups of individuals, for large groups where you measure, where you're imagining all of the things that could happen in all of the groups of that size, it will still come out as normal. Approximately. And this is called the central limit theorem. Yeah. And it's extremely useful. and very fabulous. And what it means is that most of the statistics that you do will be okay. Yeah. I'm going to stop for a moment, let you process that while I have a drink. Really should have turned off the mic there, but anyway. Does anyone want to say something at this point?
That's a normal distribution. How, for example, if you get a question like anywhere and they say, what is the distribution of this data? How would you know the difference between like an F or a Z?
Yep, that's what I'm about to talk about. I'm nearly there though, I do want to talk about another one. So at the moment I haven't mentioned any distributions that turn up when you're doing hypothesis testing. So your F and your T and your chi-squared only appear when you do hypothesis testing in this course. Okay. But these appear when you actually collect real data. Now you'll never know for certain whether anything really is normal, and you just have to go, well, it probably is normal, I'm going to make my decisions based on that. But in practice, most people don't do probability calculations for individual possums. They just do hypothesis tests with p-values and stuff. And so all of this is of theoretical interest to do what we want to do, but and in some courses they get you to calculate probabilities to do with these things, but it's not of the most important critical interest for what we're trying to do in the course that you're doing now, or in the course of actual scientific research, which is what this was all invented for. It was actually all invented for agriculture research originally. Yeah. So Fisher, who is the statistician who invented the F distribution, called F for Fisher, was working in agriculture at the time. Wheat, actually. And also eugenics, but we'll forget that. So, okay. So, that's all well and good. So now we have some situations. We have that if you just record yes or, well, where'd my, I have mixed up my pages, just a second. I've lost a page. Here it is. Right. So if you have just two options, yes or no, there's just a probability for the yes and the probability for the no, and they add up to 100%, and that's great. And if you have numerical measurements on individual objects, then they tend to be from normal distributions, and they have a mean and a standard deviation, and that's enough. A mean and standard deviation is enough information for a statistician to figure out any probability they want. What's the probability that my possum's tail length is between 10 and 15 centimetres? And they'll go, well, I'll just draw the graph and get the computer to tell me what that area is. It's great. And if you take groups of individuals and you do the mean on each of them and you imagine all the means it could have been, that will be a normal distribution as well. So there's some situations that can happen, and we can imagine probabilities. And just know that most of the time when you take measurements, most of them will be close to a middle, and then they'll be quite rare to be on either side. And that's just a good thing to know. It's what you expect, but it's not. But most measurements, it's not more likely to be on one side of the middle than the other, which is what skewed is. Okay. So there is another situation that is really common that comes up. And it's kind of like doing means. So I can imagine what one possum could tell me, and then I can imagine what a group of possums could tell me, And the distribution of for one possum was different to the distribution for the 16 possums. Of course they're different objects, but they were related to each other. But I can imagine asking a class of 250, or I can, technically this probability here belongs to one student. I'm comparing them to all the other students, but when I'm just picking one student out of the class, they either say yes or they say no, and there's a probability for yes and there's a probability for no. So what I'm doing is this event happening of the student liking cats, it either happens or it doesn't happen. But what if it wasn't a class of 250, but was all people ever, right? And some of those people don't even exist yet. And then each individual person you say, do you like cats or not? And that's a yes or a no. Still a Bernoulli distribution, I just don't know what the probabilities are this time. But what if you asked 10 students or 10 people and there was a list of yeses and nos? That's now a different object. It's a group of 10 people, not an individual person. So here's the story. An individual person likes cats, yes or no, and each of those has a probability. So there's like yes, no, and there's a probability for yes, and there's a I don't know. Let's just hopeful, be hopeful. There's a probability for yes, and there's a probability for no. Okay? It's different from wanting to own a cat. You can like cats without wanting to own one. Yeah. I like dogs, but I don't want to own one personally. Happy for other people to own them and I can visit their dogs. That's how a lot of people feel about children. That's a possibility. And so you say, well, pick a random person. Do I expect them to like cats? More often than not, yes. Okay. But what if I asked a group of like 10 people? I'm not going to draw them all. And each one of them says yes or no. The number that like cats could be anything from 0 to 10. So that's a number. This number belongs to this group of 10 people. And if I collected a different group of 10 people, I might get a different number. And if I collected a different group of 10 people, I might get maybe the same number, maybe a different number. And so there's all these possibilities for what this number could have been. That's a probability distribution. If I imagine all the numbers that could have happened and think which of them is more likely than which one, that's a probability distribution. But it belongs to the group of 10, to all groups of 10 people rather than a single person. So this is for a single person, and then here we have a group of 10 people. And there's all these options. It could be no people say yes, one person says yes, all the way up to 10 people say yes. And it'll be like, and each of these numbers would have its own probability. 1, 2, 3, 4, 5, 6, 7. Something like that. That is a probability distribution as well. And it's different from the normal distribution in that you can't get anything between 1 and 2. But with the possum tail length, you can get something between 19 and 20. That's totally possible if you had an accurate enough measuring instrument. But with this, it's not possible to get something between 1 and 2. This is a discrete distribution. And there is a name for this distribution. It is the binomial distribution. Yeah. But when I say there's more than one. It depends on how likely it is to say yes for an individual as to how likely getting 10 yeses is going to be. So if there's an 80% chance of someone saying yes, it'll be much more likely to get 10 yeses than it would if there was an 80% chance of saying no. So depending on what it is for one person will change how this works out. But that was true of my possum tail length as well. Individual possums, if their average is 15, then the average of the mean of 16 of them would be 15 as well. But if the individual possums, the average is 20, the mean would have been 22, so 20 as well. And so it depends on what the individual does. This is different to the normal distribution because in the normal distribution, you started with a number and you ended with a number. But this one, you start with a list of yeses and nos and you turn it into a number by counting them. So this is the binomial distribution. So you mentioned binomial and it turned up somewhere in the course when you're doing probability. That's the situation in which the binomial distribution appears. When you have a collection of individuals, there might be people, there might be schools, there might be days of the week. You have a collection of events and each event is either a yes or a no, and you count how many yeses there are. And then you imagine all of the different possible number of yeses that could have been. And that's the binomial distribution. And so you'll say something like, for one person, probability of like cats maybe is 0. What did I say it was before? 0.6? No, 0.4, damn it. Sad. 0.4 for 10 people if X is the number. I should change my picture to match that. Sad. If X is the number that like cats out of 10, then X will be distributed as a binomial distribution with 10 people and the probability for one person is 0.4. Or do they say bin or just B? Who knows, doesn't really matter. You can say the words binomial distribution with n equals 10 and p equals 0.4. So some people say n equals 10 and p equals 0.4, if you just to be clear. Because it's tradition for n to be the number of individuals in a group. So that's the situation when the binomial distribution turns up, when you record several times an event to see whether it happens or not, and you count how many times it happens. And that happening is called a success. And so it doesn't have to be a good thing. It could be death. You know, you go, oh, I have, you know, if I have a group of 10 rescue dogs, what's the chance in the next year that they'll still be alive, right? That they'll die? Yeah, that's a very sad one, but it does happen. So, now, we don't spend time calculating these probabilities a lot of the time, but it's good to know that there is an existing well-known formula for how to figure out these things. So I have not talked about the test statistics yet, but these are the probability distributions that go with physical situations that could happen. We've got measurements and means of measurements. We've got individual yeses and nos or groups of how many yeses and nos. They're the most common ways of producing data. And they are the probability distributions that describe those events. Right. How are we feeling? I could talk about the calculations that go with this, but I don't want to because I want to talk about the test statistics. And I may go over, and if you have to leave, that's fine. I'll just keep talking until the end to an empty room to finish it off. I'm just going to check that recording is still going. Right. Okay. So they were probability distributions that go with physical situations. Okay, there are others. If you're in an engineering course, you would learn even other ones for counting how often something happens in space or time, for example, which is a different thing again. But these are the ones that you learn in this course. Okay. Right, just bear with me. Oh, so we'll say when your lecturer creates pretend data for your assignments, they get the computer to generate things from normal and whatever distributions. That's how they do it. So it's useful to know if you want to create something that looks realistically, a crowd of individuals that looks realistic, then you can use a normal distribution to predict the numbers that you should pick. And so when people design crowds in films, they have to do that sort of thing. So it comes up in entertainment more often than you think. Okay, so, right. I'm going to switch track and say distributions for hypothesis tests. Okay. So in a hypothesis test situation, you have a yes or no question you would like to answer. And one of those answers is the null hypothesis and the other one's the alternative hypothesis. But at the moment, that's not the relevant thing I want to talk about today. So you have to choose one of those answers and imagine what it would be like to live in the land where that answer was true. So you say, you imagine where one of the answers is true, and that answer is called the null hypothesis. And it's whichever answer gives you a number that you're sure about. So if your question is the mean tail length of possums really 15 centimetres? Your null hypothesis will be it really is 15 centimetres, because that gives me a single number I can work with. But if your answer was, is the mean tail length of leadbeater possums different from the mean tail length of ringtail possums? The null hypothesis would be they are the same length, because I'll be able to do calculations by subtracting them and get the answer 0. And that's a good number that I know what it is. So if you can pitch it to be about a number that you know what the number is, that's the null hypothesis. Okay. Null hypothesis is a whole other story. I'll talk about that another day. But once you imagine the world where one of the answers is true, and then you think about the data you have collected, and you imagine all of the other data you could possibly have collected, and compare the data you've got to that. Because here's the thing. You collect data and you want to look at that data and say, do I believe that the answer is yes, or do I believe that the answer is no, based on the data I've got? That's what you want to do. Right. It helps to answer yes or no questions using data. So the only way to know whether you should believe it or not is to know how surprised you are. Like if you collected 16 ringtail possums and you got a tail length of 90 centimetres, you would be like, that's a big surprise. Right? You go, that's a huge surprise. I would have expected it to be more like 15. So you need to know how surprised you would be, which means you need to know what you think the options are. So if you want to know whether to be surprised by the data you've got, you need to know all of the data that you would have expected to get, which means you're thinking about probabilities. The human emotion of surprise is a response to probability. It's a response to something happening that you thought was unlikely. That's what surprise is about. So you imagine the world where one of the answers is true, and then you try to figure out your level of surprise at what the data was that you had, which means you need a probability. So you don't just imagine the world where one of the answers is true, you now imagine all the data that could have been collected, all the sets of data. And you compare your data to all of the sets of data that could have been collected in this world where the null hypothesis is true, and you decide whether you're surprised or not. And if you're surprised, you go, maybe the null hypothesis isn't true after all. And if you go, nah, totally ordinary, you go, right, null hypothesis could be true. I'm not unsurprised. I'm not surprised. This totally possible. So that's the idea. It's a proof by contradiction based on your level of surprise. So this is a probability situation, imagining all the sets of data that could have been collected and comparing what you've got to all the things that could have been. That's probability. That's what it's for. But that's just too hard. I just need one number. One number from my data that I compare to all of the one numbers that could have been. That's what I want. And so what you do is you calculate one number from the data and compare to all the outcomes it could have been. So we don't do that. We just calculate one number. And so I will send these notes to everybody as well. So that one number is called the test statistic. A statistic is any number you calculate from your data, and it's a test statistic because it's allowing me to test whether the answer is yes or no to my yes or no question. It's a statistic, a number you calculate from the data that you use to do a test. So the question is, theoretically, any number I calculate from my data has a probability distribution. Everything that can be written down in any situation has a probability distribution theoretically based on the philosophy of statistics. All what I need is to pick a calculation that will produce a number that I know what its distribution is so that I can figure out what the probabilities are. I can calculate whatever number I want, but if I don't know what its probabilities are, then I have no clue how to tell if I'm surprised or not. And so I need to choose a test statistic that has a distribution that I know what it is. Right. I need to choose a test statistic with a known distribution. If I am a very clever and have studied for many years statistician, I can make up a distribution. But we don't have that amount of time, so we're going to have to trust people who've done it before us. That's the philosophy of how this works. How are you feeling about that? How are you feeling about that on the Zoom? Okay not to respond. Just need to give you a chance to. Okay, so our very clever ancestors in the statistics realm have figured out, if you're in certain situations, what the best test statistic to calculate is that both that has a distribution that we know what it is, that we can actually look up, and they've fed those distributions into computers so that we can calculate them. And they are your f and your t and your z and your chi-squared. So here goes. If your research question is, you have a numerical outcome, you have a number, a quantitative outcome, and you would like to know, is the mean equal to this specific answer? And you collect data, you know, all these numbers, like that. Then the thing you should calculate is the sample mean. These are my x's. Minus the mean that I think it might be, divided by the sample standard deviation, divided by the square root of the sample size. See this standard deviation divided by root n? Because of this. Yeah, that's why it's there. All right, and so the null hypothesis is that the real mean is this number, basically. What Gossett figured out back in somewhere between 1890 and 1930, figured out was if you do this calculation and you think about all of the things that could have happened, if the original data was normal anyway, or even if it's not normal because of the central limit theorem, it'll work out probably okay, then it's a t. And the distribution of this test statistic, meaning the list of all the things it could have been and how likely they all are, under the assumption that we live in this land, because you have to pick a number for this hash, for this mu, or you'll never know what the distribution is. If the null hypothesis is true, is t with n minus 1 degrees of freedom. So if someone in a hypothesis testing situation says to you, what's the distribution of the test statistic? They want you to say a sentence like this. And that is all. You're not going to talk about shape, you're not going to talk about skewness, you're not going to talk about outliers, you're just going to say this. If they say, here is a graph of the original data, talk about the distribution of the data, then you talk about shape and whatever. But if they say, what's the distribution of the test statistic? Then this is what you say. So with my possums, 16 possums, tail lengths is the true produce a mean of 12.8 and a standard deviation of 0.7, for example. That's my example. Is the true mean length 15 centimeters? I would say the null hypothesis is that the mean is equal to 15, and the alternative is that it's not, where mu is the mean tail length. You have to tell them what the mu stands for. That's what they mean by define your parameters. Let's say what the mu or the whatever stands for. And then the test statistic is x bar minus 15 on the standard deviation on root 16, because that's what the sample size is. That's what the n that we're referring to is. And this has, if H0 is true, is the t distribution with 15 degrees of freedom. Oops, sorry. distribution I know is true is t distribution with 15 degrees of freedom. Just t with a little 15 at the bottom. Or you could say the words or t distribution with 15 degrees of freedom. Yep. Idea is that just like normal distributions, there's a different one for every mean and every standard deviation, and you need some numbers to tell you which normal distribution you've got. It's like the address to look up the normal distribution. There is a number to tell you which t distribution you've got. You only need one number to tell you which one you've got, and it's called the degrees of freedom. Don't get me started on the basket case, which is why it's called the degrees of freedom, because I still don't really understand it. But for me, I just take the abbreviation DF and it's the distribution finder. It's the address that says which of the t distributions is the one that I need to calculate the correct probabilities, because each one, the probabilities are just a little different. Just so you know, t infinity is a normal distribution. So the bigger the degrees of freedom gets, the closer to a normal distribution it becomes. Yep. So if you look up in a textbook, the table for the t distribution, it'll have a row for infinity. It's like Lord Business in the Lego movie living on the infinitieth floor. Yeah. So, that's what that is. And the t distribution, when you draw it by hand, looks to the naked eye exactly the same as a normal distribution, but the probabilities are just a little different when you actually ask a computer what it is. Yeah. But that's okay, because we don't have to draw it accurately, we just have to know what it looks like.
So if you're in say that is definitely a t,
No.
or that is definitely a normal one.
So if you're in an exam and you're looking at like a histogram, and they say what's the distribution, you'll say it looks bell-shaped.
You wouldn't say that's...
You would not say that's a t or that's a normal. Yep. You would say it looks like it might be normal, or you might say it looks symmetrical and unimodal.
So that's not even when it says compare the distribution.
Yep.
Of the distribution. It's what is the distribution? It is bell-shaped.
Yep. Yep. So if you are looking at a histogram of actual data and it says what's the distribution, then you say it looks like it might be normal, or you just say it's symmetrical and unimodal like a normal distribution, but you will not hard and fast say it is a normal distribution, because you don't know. Because to the naked eye, it looks the same as a t distribution. Who's going to know? Yeah. The only situation in which you say it's definitely a normal distribution or a t distribution is if in this situation, for a test statistic. Yeah.
So what is the distribution of the test?
That's when you say normal, t, or whatever it is. Yeah. Really important question. That's okay. It's okay to say it looks like it might be normal. But you don't say it looks like it might be a t, because, well, who knows? Which is funny, it's a really interesting thing about the way that the thing works, because in one situation you're just mega vague and you don't really specify anything, and the other one you're really specific. And that's because this is about theory and the other one's about what's actually happening, and you never really know for sure what the distribution of anything really is. In this situation, theoretically, it will be a t distribution, but that's just the same as you never really know if a die when you roll it is fair.
Can you write that down as an answer? We never really know the distribution of anything.
Yeah, you can. But for the purposes of doing this, we have to pick a distribution to do the calculation. And so what you'll do is you'll actually calculate the value of t today. This is the t that could have been, and so technically it's a capital T. The value, but it doesn't matter, nobody cares. The value of t today is 12.8 minus 15 over 0.7 on root 16, and you would get a number. Sorry? 12.8. Yes, Good move. 2.8 would be extreme, like, yeah, those poor possums. Minus 50.28, which is horribly huge. And so here is, well, no, here is all the t's that could have been and how likely they all are, and they look like a normal distribution. And the t distribution always has 0 in the centre. So these are the t's that could have happened. And this is my t all the way over here at minus 50. Like this bit here is about 2, where it's, you know. And so I would be just as surprised if it came out to be plus 50 as if it came out to be minus 50. And so the p-value is this probability down here plus the matching one at the top. But mostly a computer would give that to you, but you could ask it what TCDF or something was in R. But it's going to be approximately like 0.000, because it's very, very tiny. This number is very far away from the centre. Once it gets past 3, you just give up, right? And so that p-value is very, very small. And I say to myself, if I lived in the land where the mean really was 15 centimetres, the chances of getting a t as far away from the centre as this is wickedly unlikely. And so I don't believe that the mean really is 15 centimetres. And so because this number is very small, I reject the null hypothesis and conclude the mean is not 15 centimetres. In fact, it's probably smaller than that, because my sample came out as less than 15. So that's how a hypothesis test runs. This is the classic first hypothesis test. There is one that does a Z if you know what the real standard deviation of the original data of the distribution was, but nobody ever knows that. But yeah, just so you know. So it's like a... Yep. What if you knew from previous research that the standard deviation was for all possums was 1.2. What if you knew that? And then Z equals x bar minus the 15 divided by the 1.2 on root 60. Because that's the standard deviation that you are pretty sure it really is. And this time it's not a t, it's a z. And what z means, the distribution, if h0 is true this time, is the normal distribution with mean 0 and standard deviation 1. That's what z is. And here is my very stupid way of remembering. Ready? Here we go. Z. That's so bad. I actually don't know why they call it Z. It's probably German, like the German, yeah, German word for number is like Zahlen or something. Yeah. So, or maybe it's just because they already used X and Y for things and it was the next available letter, whatever. So but that's how I remember it. It's pretty bad.
So the Z is the normal.
The Z is the normal distribution with mean 0 and standard deviation 1. And it's called the standard normal distribution.
Helpful ways of remembering these.
No, that's all I've got. In my head, the distributions all live in a city, and the normal distributions live in the suburb of Normalville. And your mean and your standard deviation is your address, like you're on street for the mean and the house number for the standard deviation, and the standard normal distribution is in the middle. It's like it's central square, mayor's house, right in the centre. It's the standard normal distribution. It's where the train station comes out. The T distributions live in a tower block. And the degrees of freedom is the button you press on the lift to get to the one that you want. The normal distribution lives on the infinity of the floor, like Lord Business. That's distribution city. One day I will make something that little animation or something. Okay. So each situation that you're in will go with a different distribution. Most of the time, when you are working with numerical outcomes, it'll be a T, where each individual has a number to go with them, and that's when it'll be a T. But the calculation of exactly how to do that T will be different in different situations, and I don't have time to cover all of that right now, but that's the idea. So if you have a numerical outcome for each individual, and there's a situation that you're interested in, whether it makes a difference, that's a category. And so you go, is the mean different in category A compared to category B? That's like the question you might ask. So we're saying, does the category make a difference to the number, is what we're asking. Which is what the science question would be. It's like, does the species make a difference to the tail length? Right, that's how you'd say it in science. But to pitch it as a stats question, you'd have to say, is the mean tail length different for lead-bearded possums compared to ringtail possums, for example? Or is the mean tail length different for male possums compared to female possums? Is the width of the tail vein different? Which is what you really need to know as a vet. Yeah. So, and so the null hypothesis would be the mean in category A is the same as the mean in category B. And because it's a numerical outcome, we're working with means, it's going to be a T. And because we don't really know what the real standard deviation is, it's going to be a T. And so you'll say T equals X bar A minus X bar B over the square root of the standard deviation A squared on NA plus the standard deviation of B on NB. Something like that. Traditionally, it's with a 1 and a 2, but I've committed myself to A and B now. And you would say T distribution with, the computer would normally tell you how many degrees of freedom it had. And get this there is a complicated formula that produces the right number here. If you don't have a computer, you normally just pick what the smallest of NA minus 1 and NB minus 1 is. But the computer normally tells you this. And so when the computer tells you the output, it'll tell you what the mean of group A is and the mean of group B is. It'll tell you what the standard deviations are. It'll tell you what the T statistic is, and it'll tell you what the degrees of freedom is. And that's telling you the distribution. And it will be something ridiculous like 68.2. It'll because there's this calculation, even though traditionally your T statistics have to have a whole number, there's nothing stopping the mathematical formula putting a not whole number in that spot. And so they go, well, if I'd picked this not whole number, the numbers would work, the probabilities would work out more accurately. It's very clever and weird, but there you go. And so generally with a numerical outcome, you'll get a T. And so when you are comparing two groups with a T, when you're doing regression, there'll be a T. There's just, in general, a T is an indicator, a T is the thing that'll happen if you're doing a test statistic for a numerical outcome. That's when there's a numerical outcome for each individual. If each individual has a yes or no outcome, and you're trying to find out whether the probability of that outcome is different in different situations, that's when you use a Z. So if you've got this, does category A or B make the outcome yes or no more or less likely, then you'll get a Z. And the Z will be from a normal distribution with mean 0 and standard deviation 1, because that's what Z means. So this is for the null hypothesis, is the probability in situation of yes in situation A different to the probability, the same as probability of situation B. But if you're looking at multiple categories, you know, A, B, C, does that make a difference to the yes or no? You'll do a chi-squared test. We have this little table that's got like A, B, C, yes, no, and there'll be observed and predicted values and that sort of thing. And the chi-squared statistic will come from a chi-squared distribution with 2 degrees of freedom or some other number. And that's because when Pearson invented this test, this is the correct distribution to look up the probabilities in. And the chi-squared distribution looks like this. It's skewed. And last but not least, the F statistic happens when you do ANOVA. And that's when it happens. And ANOVA is this situation. You know, more than 2 categories. And so you do ANOVA and you get an F statistic. And the F statistic comes from an F distribution, and it will have 2 degrees of freedom. So the T statistic only has 1 number for its degrees of freedom, but the F statistic has 2 numbers for its degrees of freedom. Because it's actually 2 T statistics that are divided by each other. So it doesn't look like it is, but that's what it really is. Actually, it's technically 2 chi-squared. No, it's 2 chi-squared statistics divided by each other, but that's a whole other story. But this is the only situation that you get an F when you do ANOVA. So when you do regression, technically there's an ANOVA there, and if you ask R to do regression, it will tell you an F statistic as well, and that's because it's done ANOVA to compare the outcome across all the possibilities. But analysis of variance is when you get an F statistic, and that's what it's for. But you still make the same decision at the end. The p-value being less than 0.05 or whatever is when you declare that the null hypothesis is false. Well, that's when you declare that you have strong evidence to suggest that the null hypothesis is false. Yeah. So with F or with chi-squared or with Z, if the p-value is under a certain number, you say there is strong evidence to suggest the null hypothesis is false. Strong evidence to reject the null hypothesis. So you know how they say reject or retain? Yeah. You're supposed to say, it's fine in this course, but you're supposed to say, there is strong evidence to reject the null hypothesis, or there is no evidence to reject the null hypothesis. You never say it's true or false, you just say, I have evidence for or against. That's going back to the very beginning where you're never hard and fast about anything in statistics. You always say, there is evidence for, or it appears that. Yeah. Except in this situation where you say the distribution is an F statistic, like F distribution. So they're the distributions. T happens when you've got a numerical outcome with up to 2 categories. The F happens when you've got a numerical outcome with 3 or more categories, with ANOVA. And the chi-squared, the Z happens when you've got a yes or no outcome. Or when you've got a numerical outcome when you know the real standard deviation. That's the special case. And the F chi-squared happens when you've got categorical outcome with more than 2 categories. Or you've got a table, right, like this. That's the chi-squared. And the F happens when you do ANOVA. But all of these ones that have letter names, F, T, chi, Z, all of those ones that have letter names more or less only appear when you're doing hypothesis tests. And so if you're looking at data from a sample, you don't mention any of those things. You just say it's unimodal and symmetric or whatever. But if you're asked in a hypothesis test situation, what's the distribution? It will be one of these options. That is enough, I think.
So the chi-square was categorical with tables. Z is if there's yes or no, or in the case of numericals, if you have the real standard deviation.
Yeah.
F is ANOVA or regressions, variance with more than 2 categories. And T is numerical.
Or just one. Like numerical outcomes with up to 2 categories. We can talk more about this in the intervening time. This is all wrapped up in the decision of which hypothesis test to do. But they are pretty much those are the decisions in this course. Pretty sure you did chi-squared.
Yeah, it was in the last.
Yeah, it's usually the last couple of weeks.
Yeah, when they're almost distributed.
Yeah. And it's a pretty, Pearson was very clever to come up with this calculation. I have no idea what inspiration he had for that. That was just amazing. And technically you can do chi-squared in this situation, but usually you're not interested in that. So it depends on how they pitch the question. Because this question is, are these 2 categories, 2 different categorical variables related to each other? Whereas this one is, does this situation make a difference to this probability? So that yes or no outcome belongs to the individuals. So even though you might write down the percentage that came out with a certain answer, that is a number, but it doesn't belong to any one of the people. The individual people all have just a yes or no. That's what I'm talking about with the yes or no outcome. All right, time to stop. Thank you. You were very nice.